So this is our very last one in additional physics on car safety. There's a few things to learn in this, but actually mostly it's about applying the ideas from the other parts of the unit. So we need to learn this really, the two parts of stopping and what affects them. And then after that, we're just interpreting speed time graphs, so a sort of specialist example of speed time graphs for car stopping, but with the same ideas that you've talked about for speed time graphs earlier. And then we need to explain safety features of cars, talking about Newton's laws and how they're applied to car safety. So, first things for us to talk about is stopping distance. There are two parts of stopping distance. So, if somebody runs out in the road in front of you when you're driving along in your car, the first thing that happens is you have to react to thinking that you need to actually get your foot on the brake. And of course, while you're doing this, your car is still travelling along the road. The longer it takes you to think, oh dear, I better get my foot on the brake, then the further you're going to go before you actually start slowing down. We'll call the distance that you travel while you're doing this your thinking distance. Once you've got your foot on the brake, of course, you don't stop instantly. You're going to carry on along the road as you slow down. So the distance that you move after you've applied the brakes is called the braking distance. Add these two together, then we end up with a distance called the stopping distance. Okay, it's a bit easy if you're not careful to get confused between stopping and braking, but remember the stopping distance is the total distance it takes you to stop. The braking distance is the distance you move while you've actually got your foot on the brake. You've got to add on the thinking distance. Okay, so there are various things that might make it dangerous when you're driving. Some of these things will increase the thinking distance, some will increase the braking distance, and one of them will increase both. So if you look at these examples, they might ask you in the exam to state an example of something that might increase your thinking distance or increase your braking distance. Or they might just ask you one of these, which does it increase? So if you've got alcohol in your system, then the chances are it's just going to slow your reactions down. So you might well brake just as well once you've got your foot on the brake, but alcohol in your system slows down your action, so it's going to increase your thinking distance. Having poor tyres on your car isn't going to make any difference to how long it takes you to get your foot on the brake, but it is going to make the car not brake as well once it is slowing down, so you might get less friction on the road and slow down more over a longer distance. Okay, drugs is just another specialised example. Obviously, alcohol is a drug, so it's just, again, slowing down your reaction times. If the road is icy or wet roads might go into that category, then again that's going to increase your braking distance if you slide on the road. If you're not concentrating, if you're on the phone for example, then that's going to increase your thinking distance. And then the one that catches people out normally is speed. You might guess where speed's going, but even if you've got the same thinking time, the distance that you travel is going to be longer if you're going faster, and also the faster you're going, the longer it's going to take you to stop. So speed actually increases both the thinking and the braking distances. So that's why speed is so dangerous, because it's going to increase both halves of this stopping. So if we think about how this is going to look on a speed time graph, the crucial thing to understand here is that as we start off, the speed is going to stay the same in this section of the graph until we've got our foot on the brake. So we've got a constant speed, and then we get our foot on the brake, then we slow down. They never make it too complicated. We just assume that the car has got a constant deceleration, that your brakes are working with the same force all the way through. So our speed time graph looks like that. If we try to relate those last two things we talked about, this distance under the speed time graph, remember the distance under the area under a speed time graph is the distance travelled. So this part here, the green part, is the thinking distance. This is how far you go before you get your foot on the brake. Then you get your foot on the brake. That's the braking distance. Thinking about the equations for these areas, the thinking distance is just the speed times the time. This is a rectangle, so we just need to know how fast we're going, how long we're going at that speed for before we get our foot on the brake. Braking distance a bit more complicated because we've got a triangle. Okay, but I'm sure you'll remember from your maths, triangles are half times the base times the height. So we've got a half times the speed here times the time it takes to stop. Just be careful on this one. This time to stop If you've got a number over here, you've got to take away the number here. I'll show you an example here. So here's an example of a graph. This is somebody who's driving at 20 meters per second. It takes them half a second to get their foot on the brake, and then another 2 seconds altogether to stop. So 2.5 seconds is the total time it takes to stop. Half a second to react, 2 seconds after you've got your foot on the brake. So to work out their distance, their total stopping distance, we've got to work out the thinking distance. So that's just the area of this rectangle, so that's just 20 times 0.5. So 10 meters before you've got your foot on the brake. After you've got your foot on the brake, okay, we've got the time is 2 seconds. So this gives us an acceleration of -10, okay? We don't need to work that out for this, but the braking distance is a half times 20 times 2. So 20 meters after you've got your foot on the brake. So the total stopping distance is 10 plus 20, 30 meters. Okay, looking at the pattern of these things, here's a table taken out of the highway code. If you're doing your theory driving test in a year or two, you might have to learn these numbers. So these are speeds in miles per hour, so this isn't what we'd usually use. But here's the thinking distance in blue and the braking distance in red. They've put this blurry line in between them because obviously you start to sort of push your foot on the brake. It takes a little bit of time to get the brakes fully applied. But we can just imagine this as 9 and 14. If we're looking for a pattern, you'll notice that the thinking distance has got a nice simple pattern because it just goes 9, 12, 15, 18, 21. So what we can say is that the thinking distance is proportional to the speed. But if we look at braking distance, okay, the braking distance at 30 miles an hour is 14 meters, but by the time we've got to 60 miles an hour, twice as fast, it's basically 4 times the distance at 55 meters. So the thinking distance is proportional to the velocity, but actually the braking distance goes up much quicker. If you think about kinetic energy, when the car's going at 60 miles an hour, its velocity is twice as high. Kinetic energy is a half mv squared, so its kinetic energy is 4 times as big. That's why it takes 4 times as far for the brakes to stop the car. So another reason that speed is so dangerous when you're driving. You think if you're going twice as fast, it's going to take you twice the distance to stop, but actually the total stopping distance is over 3 times as far. So the last part of our video is about what happens if you do crash. What can we do to keep people safe when they do crash their car? Well, thinking about Newton's law, Newton's first law says that if the car stops, that doesn't mean you're going to stop, you're going to carry on. So in a car crash, the person inside tends to just carry on moving until they hit something. And Newton's second law says that the force that's applied to them, it's the force that's going to kill you at the end of the day. Depends on how fast you lose your momentum. So a little video to show you about Newton's first law, a bit gory.
Richard didn't want to die, but he couldn't stop himself. The collision with the car didn't kill him, but he wasn't wearing a seatbelt, so he continued on his journey. When he hit the inside of the car, that didn't kill him either. But his internal organs carried on travelling until they hit his rib cage, and his lungs were punctured, and the main artery from his heart was torn. And that's what killed Richard.
And then we need to think about how you can lose your momentum over a longer period of time. The longer it takes you to lose your momentum, the less force you'll have to put on you. So there are 2 areas where this is done really. Crumple zone, so this is a part of the front of the car which is designed to crumple up. Okay, if you see a car in a car crash and you see all the front caved in and you think, oh, that's not very good, they should have built the car stronger. Well, in fact, it's just the opposite. That piece is designed to crumple up to make it take longer for the car to stop, and therefore the longer it takes the car to stop, the longer it takes you to stop, and the less force you need on your body. Likewise, seatbelts are for the same thing. The seatbelt is designed to stretch and make you take as long as possible rather than you flying forward until you hit the steering wheel or the dashboard and stopping very suddenly. We can apply some actual mathematics to this. So if you're going to lose your momentum, think about the momentum of a 50 kilogram person travelling at 20 meters per second. Momentum is the mass times the velocity, so we're doing 50 times 20 is 1,000 Newton seconds. You've got to lose this, and the way you lose momentum is the force times the time. So your choices about how to lose your 1,000 Newton seconds of momentum are either to have a very big force for a short time, which is likely to kill you. 10,000 Newton force is quite a big force to have on your body. So you can have 10,000 Newtons for 0.1 seconds if you stop very quickly. But if you can make it take a whole second to stop, okay, then you can have 1,000 Newtons for a whole second. Okay, the same change in momentum, but the force is only a tenth as big, and therefore you're much more likely to survive the accident.
Key to its defences is its so-called tritium safety cell, a rigid steel cage reinforced at key points. Smart described it as the hard shell of a nut, with small but efficient crumple zones both at the front and at the rear. In theory, getting inside is like putting on a suit of armour.
The downside of the shell's rigidity is that there's a greater potential for the crash forces to be transmitted through to the passengers. Ideally, you want to slow them down as gently as possible. So, you get seatbelt tensioners that stop you lurching forward violently, and they're fitted with force limiters that give you a bit of slack before they dig into your chest. The car's also fitted with a driver airbag, a passenger airbag, and a steering column that will retract out of the way in a crash to give you more room to slow down.
That's the theory, but no one knows how the car will behave when it's crashed at 70 miles an hour, which is where we come in. From 70 miles an hour to naught in 1 second. Energy that had moved 20 tons of concrete, leapt into the air and rebounded to the side of the road. We didn't know what we'd find when we reached the wreckage. The steel cage has certainly done its job really well. You can still see the original shape, just that one nasty kink there. Don't forget, this is a car without a roof. The plastic was just shattered. So without even the strength of the roof, there hasn't been that much effect. You can in fact open the door. Bits fly out. And I tell you really, when you come around the front, you do see that massive impact. Around the other side, though, it still looks remarkably like a smart car. You can see the full shape of the door. Indeed, the door not only opens normally, closes again. So that does show how well that cage has worked on this impact.
We were staggered at how well the Smart seemed to have stood up to our high-speed collision, but couldn't help wondering how a conventional small car would have performed in a similar test. But here's the rub. The cars may have stood up to the severity of the crash surprisingly well, but the humans inside wouldn't. No matter what you drive, rapidly decelerating from higher speeds is something your internal organs simply cannot cope with. The chilling truth is, the people inside both cars would have been very unlikely to have survived.
So, how much stick can a Smart take? A lot. But that can't be said for its passengers.